Hi, very good morning, students. And today we are going to deal a new content or some theories. From now onwards, we will be starting with the theories. There are many theories like valency bond theory, Vesper theory, that is valency shell electron pair repulsion theory, molecular orbital theory, and so on, right? And all these theories will be explaining only regarding the covalent bond. Okay? All the theories whatever we are going to learn will be explaining only regarding the what covalent bond only. Yes, in the previous lecture we have drawn something with respect to Lewis dot structures, right? Lewis scientist was able to explain the structure of the molecules. He was able to explain the structure of the molecules, but failed to explain the geometry of the molecules. Okay, don't get the confused with the structure and the geometry. I'll be explaining in clear. Okay, whenever we'll come with respect to hybridization, we'll be learning to know that. So he has explained the structure. One molecule will be having what type of structure, but he could not explain the geometry. Okay, we'll be going in detail, right? Okay, till for now you remember that geometry and structure are different. Okay, all theories were said for only covalent bonds. And if you go for the VBT theory is also called as valency bond theory, and this theory talks about overlapping of atomic orbitals. See, not molecular orbitals, only atomic orbitals, because you have one more theory that is called as MOT, where molecular orbitals will be combining. Here, VBT talks only with respect to the atomic orbitals, and this was first time it was introduced by Mr. Hitler and London. These are the scientists who first proposed the valency bond theory, and it was further developed by Mr. Pauling and Slater. These are the two scientists who developed the concept which was proposed by Hitler and London. So when you go to the rules, what are in valency bond theory means? Covalent bond is formed by the overlapping of atomic orbitals. What it says? So atoms combine together, means atomic orbitals of an atoms combine together and they overlap together, they form the bond. That bond it is called as covalent bond. Covalent bond is nothing but sharing of electrons. So for the formation of the covalent bond, what should be for the atoms? The atoms should be very close together, right? Only half-filled orbitals with electrons of opposite spin overlap. So for the formation of the bond, you should be having atomic orbital, and that atomic orbital should be with half-filled electrons. It should not be completely filled, and that too the spin should be opposite with each other. Suppose if two atoms are having half-filled electrons but they are with parallel spins, they will not overlap. Okay, parallel means the electron with both are present in the same direction, like this. If we have like this electron, this is in one direction, upward direction, this is also upward direction, so we have like this, then that is called as parallel spin. Opposite spin means one should be in the opposite this way and that should be in this way, right? Okay, students, for the formation of the covalent bond, the atomic orbitals should be half-filled as well as the electrons should be in the opposite spin. And the overlapping, they will be overlapping, right? When the overlapping occurs, more than 50% overlap should not occur. Okay, if more than 50% occurs, what happens? If 100% happens, two atoms combine together and they form a single atom. There are no two atoms again. So always overlapping will not be greater than 50%, right? It must be the overlap for the formation of the bond, that is covalent bond. It should be less than 50%. Okay, when it is greater than 50% or equal to 50%, repulsion comes into the existence, right? Okay, extent of overlapping. If more is the overlapping, the bond strength will be very higher. Okay, see, more is the like this, they will be overlapping, right? If only some overlapping, weak. If it is going more, it is more. If it is still going, still harder. So in this way, if the extent of overlap is very high, the strength of the bond will be very high. If bond strength is very high, to break that bond, you require more amount of energy. So more bond energy will be present. If they are very close together, means what happens to the bond length? The bond length will be less. This is the criteria. More is the overlapping, more is the strength of the bond, more will be the bond energy, and the length distance between the two atoms will be very less. Okay, these are the rules what they are saying. The two types of the overlaps which are possible. So we are saying with respect to overlapping, right? Two types of overlaps are possible. One is axial overlap, means head-on-head overlap. This is also called as head-on-head overlap. This axial overlap forms sigma bond. See, one-on-one overlapping, that is also called as head-on-head overlapping, and this head-on-head overlapping results in the formation of the sigma bond, whereas the parallel overlapping means they will not overlap one on the other, or it is called as sideways overlapping, or it is also called as lateral overlapping. Okay, parallel overlapping or sidewise overlapping or lateral overlapping, and this sidewise or parallel overlapping results in the formation of the pi bond. See, axial overlapping results in sigma bond, parallel overlapping results in the pi bond. And the overlapping must have same signs. So whatever the orbitals that are getting overlapped with one another, they will be having same signs. Plus will overlap with only plus, minus will overlap with only minus. Don't go for the mathematics or application rules with respect to physics. Plus will combine with plus repels with the plus, plus attracts the minus. Don't go that thought of thinking. Okay, in chemistry, one orbital with a plus sign overlaps with the other orbital with the same sign. In the same way, negative overlaps with the negative sign. What does the plus indicate? It indicates crust. Negative indicates trough. So no overlap between the plus and minus. Okay, orbitals. Among plus and minus, proper orientation is required. Not only the presence of that one, and orientation also is also required. We will learn regarding this in chemical kinetics. Right. I will be showing with the pictorial representation regarding the overlaps, whatever that I have said till now. So this is p orbital. This is moving in a dumbbell shape. This one also in the dumbbell shape. See, this is one is taken as the plus sign, other is taken as the minus sign. Here also p. In one orbital it is taken. So this is one orbital only. One lobe it is taken as plus sign, other lobe it is taken as minus sign. Right. As I am taking this is px. Means the orbital is along the x-axis. Here also I am taking the same orbital which is overlapping with the x-axis. Okay. If these two combine and they form px of one orbital and combining the px of the other orbital, and these two resulting in the formation of the sigma bond, means they are overlapping one on the other, so that they will be getting like this, or it will be both plus or may be present, or both minus may be present. Okay, that is with pp overlapping resulting in the sigma bond. Next, py. See, py means it will be along the y-axis, px means along the z-axis. See, here there is no orientation. Already I have said, orientation it will be dealt in chemical kinetics perfectly. Till now, for this time, you remember that an orbital is along the py and the other orbital is along the px. Means one orbital is present along the x-axis and the other orbital is present along the y-axis. Among these two, there will be no overlapping. So, because there is no proper orientation between the atomic orbitals, so there is no formation of the bond between the two orbitals which are in the other orientations. So, if you go for the two types of overlappings, first one is head-on-head overlapping, or it is also called as axial overlapping. We can find this head-on-head overlapping or axial overlapping in these type of orbitals. Yes, one s orbital combines with the other s orbital, forming in the head-on-head overlapping. Same way, one s orbital combines with the p orbital, forming in the sp overlapping, that is head-on-head. One p orbital combines with the other p orbital, results in the formation of the head-on-head overlapping or axial overlapping. So for SS we are seeing s orbital, this is present, this is also s orbital. These two are combining and they are combining like this. Okay, here there is a formation of the bond. This is sigma bond. That is also called as something like covalent bond, because that is shared between by these two atomic orbitals. So s orbital always forms only sigma bonds. There is no s orbital which forms pi bond. There are only orbitals which forms only sigma bond, because it is spherically symmetric. Only possibility completely it is spherical in structure, so that it overlaps on the other. It results in the formation of the sigma bond. There is no formation of the pi bond with respect to s orbital. And as it is symmetrically or spherically symmetric, it is a non-directional in nature. It doesn't have any particular direction, so it doesn't form any sigma bond. S orbital can never form pi bond, whatever I have said. I am taking this one example showing in H2 molecule. See, H2 means how many atoms do you have here? You are having two atoms, one hydrogen this one hydrogen this one. See, I am taking, what is the configuration of hydrogen? It is 1s1, so I am taking this one orbital. For this hydrogen, this is 1s1, I am taking this orbital. See, this one, yes, I am representing spherically hydrogen atom of this one. It is, are we having s orbital spherically, one electron, I am taking this pattern. This one, see, atomic orbital, this is one atom, this is one atom. These two atoms are combining together and they are forming the molecular orbital. Atomic orbitals combine together and they form molecular orbital. Okay, and here the formation of bond is sigma bond. See, spin of electron, one is in the upward direction, one is in the downward direction. If both are in the same direction, again there will be no overlap. Getting this, students? Atomic orbitals and the spin of the electron should be opposite direction. Then only there will be formation of the bond. Right? Suppose if I take the HF molecule, hydrogen, it is represented as 1s1 in this way, so it is S. For fluorine, 1s2, 2s2, 2p5. So 1s2 in this way, 2s2, 2p5. which will be involved in the bonding. Already I have said only unpaired electrons. So only this one will involve in the formation of the bonding. What is this? This is p orbital, right? P orbital shape is in this pattern, dumbbell shape. Hydrogen it is spherical one, right? Yes, it is overlapping with the p, and electrons are in the opposite direction, right? So these two overlap, and this results in the formation of the sigma bond. So what type of sigma bond? This is 1s, and this p orbital belongs to 2p, right? So sigma, we can call it a sigma 1s 2p overlap. Here I have written sigma 1s 1s. So like this, we are getting sigma bond, sigma 1s 2p. There is a formation of the sigma bond between 1s orbital as well as the 2p orbital. Okay, right. Let me take one more example. See, here we will be having HCl. Try to draw that, students. HCl, HBr, HI. So HCl we will be having 1s, Cl will be having 3p. So sigma 1s 3p. For HBr, sigma 1s 4p. For HI, it is sigma 1s 5p. So first formed bond always is sigma bond. After that only 5 bonds are formed. What does this indicate? It indicates that if there is a molecule, first if there are any pi bonds, first there should be formation of only sigma bond. After formation of the sigma bond only, there will be the formation of pi bond. Remember this, students. After the formation of the sigma bond only, there will be the formation of pi bonds. Okay, there is exception like C2. Only that is exception till now we have seen. We will be having that. Okay. So first formed bond will be always sigma bond, and it is very strong bond when compared to the pi bond. Okay. When n is principal quantum number, suppose n, this one here, 1s, n is 1, for 3p it is n is 3, like this. When n is low, okay, or when principal quantum number is low, that bond will be closer to the nucleus and bond strength will be very high. Means, what he is saying, when the orbital is very closer to the nucleus, see, among 1s and 3p, 1s and 4p, 1s and 5p, which will be stronger? The stronger one will be 1s and 3p. Because this one 3p is very closer to this one. When compared to 4p is one shell away from this, and 5p is one more shell away from that. So whenever it is closer, the strength of the bond will be very closer. In the same way, students, try to do this. Which bond will have more bond energy? HF, HBr, HCl, HI. See, in this case, 1s 2p. Here 1s, what happens? 4p, 1s 3p, 1s 5p. Okay, students. So A will be the answer because the strength is very high, and the order is, see here, all 1s as well as 2. Okay, 2p, 1s 2p. This one here, when you compare 1s 2p with the 2p 2p, 1s 2p is greater, and 2p 2p when you compare with 3s 3p, 2p 2p is greater. Okay, so whenever the overlapping is very closer to the nucleus, then the strength of the bond will be very higher, right? In the same way, if I take two p orbitals, so these are the p orbitals. These two are getting overlapped. See, plus sign is combining with the plus sign, so that it is forming this one, so that there is a formation of the sigma bond. Okay, students. See, in this way, I am taking two orbitals. Here, what happens? These two are getting overlapped in this way. This is not sigma bond. Remember this. You are having two sides. Okay, one is above and one is below the plane, and this dotted one indicates the nucleus. This overlap, it is called as pi overlapping. So this is not head-on-head overlap. This is axial overlapping. Okay, two lobes are overlapping sideways. See, their sides are overlapping. Here, see, their orientation is overlapping. Here, sides are overlapping. When the sides are overlapping, this results in the formation of the pi bond. Okay, students, let me take one example. BF3. If you take boron configuration, boron atomic number is 5. If I take this general configuration, it is 1s2, 2s2, 2p1. This is the ground state configuration. I am writing for the only valency shell. For 2s2 it is 2s2, 2p1 it is 1. See, but in BF3 we are having 3 bonds. Okay, B is linked with the 3 fluorine atoms. But you are having how many unpaired electrons? Only 1. Means you should be having 3 half-filled orbitals in boron. But here you are having ground state only 1. So provide some amount of energy so that the electron, whatever that is present in this, get excited. So that what you will be having? Now you are having 3 unpaired electrons. Okay. As there are 3 fluorines, I am taking 3 fluorines, F1, F2, F3. Okay. Fluorine configuration is in this pattern. 1s2, 2s2, 2p5. 2p5 I am representing here in this pattern, 2p5, 2p5. So 1 electron here is here. 1 electron of the fluorine combines with the 1 electron of boron. Here 1 more electron of fluorine combines with 1 more electron of boron. 1 more electron of fluorine combines with the 1 more electron of the boron. So what happening? How many sigma bonds are formed? So there is a formation of 3 sigma bonds. See boron. Okay. In boron, see, you are having 2s electron, right? 2s it is combining with 2p, 2p with 2p, 2p with 2p. So boron 2s is combining with the 2p, fluorine, this is sigma. Boron combining 2p with fluorine 2p, forming sigma bond. Boron 2p combining with fluorine 2p, forming sigma bond. So this is the structure. The question may be like this: how many sigma 2p 2p bonds are present in BF3 molecule? So it is 2. Okay. Right, students, let us take one more example. I am going for the molecule like H2O, and hydrogen it is represented as 1s1. As we are having 2 hydrogens, one more hydrogen it is 1s1, so 2. Oxygen it is 1s2, 2s2, 2p4. So valence shell I am representing it as 2p4 in this pattern. Okay. So how many are there? 2 unpaired electrons. You are having 2, so it is enough. No need to go for the excited, right? So here p orbital is present. One orbital, see px, py, pz. Px already it is filled up. We can fill up anything, nothing happens. Py and pz are present. Okay. Py this is the condition, and pz this is the condition, because those two are all these three will be perpendicular to each other. Okay. So what is happening? In pz you are having 1 electron free, and py you are having 1 electron free. So hydrogen is having 1 electron free, that combines with the py as well as pz. There is formation of 2 sigma bonds. Okay. Between what? Sigma bond is formed between this one. This sigma bond is between 1s of hydrogen with 2p of oxygen. This one same, 1s of hydrogen with 2p of oxygen results in the formation of 2 bonds. Okay. Next it is sidewise overlapping. It is also called as parallel overlapping, or it is also called as lateral overlapping. See, axial overlapping, where we can see the axial overlapping in SS, PP as well as SP. But lateral overlapping we can't see in S orbital. We can see only in PP, PD, DD. Okay, as it is forming pi bond, we have indicated with p pi, p pi, p pi, d pi, d pi, d pi. Okay, right. So I am showing here we are having p orbitals. Already have mentioned this p orbital. These two are combining sideways, forming in the formation of the pi bond. Okay, if you see the O2 molecule, okay, we are having O2 molecule in this pattern. So generally, if you write, you are having 2 oxygens. One oxygen configuration is in this pattern 1s2, 2s2, 2p4. Other oxygen atom configuration is 1s2, 2s2, 2p4. See, py, pz. In the both the oxygen atom, you are having the 2 unpaired electrons. Okay, so totally, what happens? One among these two, px, pz may be overlapping sidewise, and the other one is resulting in the formation of the pi bond. So how many pi bonds you will be having? See, one pz of this oxygen atom, other pz of this oxygen atom combines together and they form this sigma bond, means they are resulting in the formation of, see, pi bond formation. I have already said pi bond formation will occur only after the formation of the sigma bond. Okay, so as we are having 4 electrons, how many bonds you should be formed? You should be forming 2 bonds. Among the 2 bonds, first formation bond is sigma bond. So first sigma bond is formed among pz, pz. See, you can make a sigma bond between py, py also. Pz will form pi bond. Nothing will happen. Anyway, you can take. So as I have taken pz is forming the sigma bond here. The other py, which will be in the parallel way, they will be forming pi bond. Right? Don't think that 2 pi bonds are formed. It is either above or below plane, since electrons is a wave. Okay, don't think that, see, it may be overlapping upwardwise or downwise. You will be thinking 2 pi bonds are there. No, there is only 1 pi bond, because as the electron is a wave, will not be moving like a particle. It will be moving like a wave. If it is present at the top side, you will be getting the pi bond on the top. If it is on the bottom side of the sigma bond, you will be getting the sigma bond at the bottom. In the same way, students, I have drawn for the one more thing for N2 molecule. This is the structure. You are having 2 nitrogens. Configuration is 1s2, 2s2, 2p3. The same way for the other nitrogen. In each nitrogen, you are having 3 unpaired electron. So among these 3 unpaired, one results in the formation of the sigma bond. Okay, among one will be formed px will be forming the sigma bond. You will be having 2 unpaired electrons in each of the nitrogen. Those two will overlap sidewise, forming the pi bond. Okay, right, students. In this molecule, you are having 2 pi bonds. In the same way, students, this is the homework for you. Find the number of sigma bonds and pi bonds in H2O molecule, NH3, C2H2, C2H4, CH3COOH, SO3, H2SO4, C2CN taken 4 times, C6H6. Okay, already I have given all the structures. These are the structures of these molecules. Don't get confused how these are present. The way of drawing the structure also we'll be learning at the end of the chapter, that is in the topic called as hybridization. So go for the calculating of the sigma bonds as well as the pi bonds present in the molecule. These are the example, students. Thank you. This is for today. Have a nice day.